Okay, everybody, thank you for joining us at this first talk of the day about embedded Linux security. Now, at risk of being accused of getting my excuses in early, you can probably tell that my voice is not functioning at 100%, so I will do my best to get through the next hour. I hope it's not too irritating to listen to me scratching around somewhat. So I will do my best. If I have to break off and have a coughing fit, then apologies in advance for that. I've got plenty of supplies here, so hopefully this will keep me going. So welcome to this very brief overview of some of the topics related to securing embedded Linux systems. Just a word about myself. My name is Simon Goda. I work for a company called Doulos, who are a training company, pure training company. We don't do consultancy. We're based in the UK with subsidiaries in Germany and the US, and we like to think the market leaders for providing training in the hardware side of things, design, Verilog system, Verilog, all of that sort of stuff, and in embedded systems, operating systems, tools, programming, that sort of thing. So for my part, I've been with Doulos for, just over 10 years now. Prior to that, I worked for a semiconductor company called ST Microelectronics, working on operating systems, tools and related topics. So I've been messing around with embedded Linux and embedded Android systems for well over 20 years during my career. So what we're going to take a look at are some of the background issues, some of the rationale behind the need for securing a system that's running embedded Linux, some of the standards that are in place, and we're going to pick on one of those standards as a kind of framework to hang our discussion on, if you like, and look at some of the fairly standard features of an embedded Linux system that we can use to help satisfy those types of standards, the requirements of those types of standards. So we'll introduce security at the high level, why we need it. We'll then start looking at some of the things we can do around the compilation of code and some of the tools that we have available. We'll look at some of the features of Linux that we can use to secure our system. Look at the kernel. Obviously, the heart of an embedded Linux system is the Linux kernel. What features does it have that we can use to make our system more secure? Look at the boot process. And very briefly at the end, just really a one-slide mention of vendor support. As we'll see, the silicon vendors are very active in security, and it's something not to dismiss. So looking at the background, if we think about the role of security, it's going beyond the intended use of a particular device. A device can be functionally correct and do what it's supposed to do, but still be deeply insecure. And so security of a device is going beyond that correctness and looking instead for things like flawed design or weaknesses in software that mean that device could be misused in some way. And people who are attacking these devices are looking for flaws or weaknesses that they can exploit, often not because of the device itself, but because of the space that device operates in, the interactions that it's having. We can see in the picture, a device, whatever it might be, is interacting with users, with other devices, with other things, potentially with cloud services. It's handling sensitive data. And the aim when we're making a device secure is to protect all of this, not just the device itself. So one of the best ways that we can kind of understand how a system can be attacked is to create what's called an attack model. This was an idea that originally came out in what's called an RFC 4949, Internet Security Glossary, which was published in 2007, but is very applicable to devices running things like embedded Linux. It provides definitions of terms. It provides a way for us to think about how our device operates and what risks and attacks it could be subject to. So we can carry out an analysis of threat. Who might want to attack this device? Why would they want to attack it? What are the entry points, or sometimes called attack vectors, that may be available to them? What interfaces does this device present? Is there a point where the user has to type in a password? That's an obvious attack vector into that device. What exploits might be required? What degree of technical competence might be needed? Do you need to be a hardcore hacker in order to be able to exploit this device? Or could, someone with zero knowledge just kind of do this by accident? We also need to think about the risk. What assets are under threat? What is the consequence of an attack taking place? What vulnerabilities do we know are already there in this device in terms of the hardware and the software? Often all of this process is called threat modeling. It's about putting together a kind of big picture of the device. And one of the pieces of advice that we find very helpful is, if you're developing a product within a development team, it's very useful to treat this as a group activity. The whole team can get involved. It's a whiteboarded activity, if you see what I mean. Everybody's input can help bring out the full picture of the potential threats to your device. What we have in the industry or the different sectors is a whole proliferation of different standards and guidelines. It strikes me as being in many ways quite easy to write a standard or a set of guidelines. The difficult bit is actually doing it and putting into place these provisions that these things lay out. A really useful website I find is this one, iotsecuritymapping.com, which was put together by a UK security consultancy, Copper Horse. And what they do is they map all the different standards from different industries all around the world onto a set of provisions which were laid out originally by the European telecommunications standards industry, known as the ETSI 303645 standard, which lays out 13 provisions that will make, if you follow these provisions, your device should be secure. And you can see, you don't need to see the detail on that, but the center blob is one of the ETSI provisions, and then all of these blobs around it are the different international standards that feed into basically say the same thing as that ETSI provision. It's really worth looking at the website. It's very dynamic. You click on one of the standards and it will bring out the actual text that matches the ETSI provision. It's a really useful website for kind of visualizing just the vast array of documents that we have that more or less say the same thing. So these are those 13 ETSI provisions. Most of them are kind of common sense, but the fact that they felt the need to write these things down does imply that these things have been problems. And in fact, if we look at these different provisions, I'll go through them in a moment, I'm sure we can all remember cases where these things have been a problem. So, no universal default passwords. It's still done now on devices. You can buy a product off the shelf and there'll be a slip of paper in it that says the password is pass123. Keep software updated. Of course, you need to have a mechanism to keep your software updated. If you don't have that mechanism, that's implying that you believe that your software is perfect and has no bugs and no security vulnerabilities. Communication must be secure. The software integrity must be ensured, i.e. It shouldn't be possible to change software on that device without doing it through the proper channels. You must be resilient to outages like power outages or network outages. You must make it easy for users to delete their own data and properly delete it not just make it look like it's been deleted. Input data must be validated. This is a very common source of problems. Something so trivial as entering a string into a box on a website can be the cause of many, many problems. Looking at the second column, implement a means to manage reports of vulnerabilities. What if you detect something wrong with this device? How do you tell people? How is that made public? This common sense at the utmost here, securely stores sensitive security parameters. You can't get any more common sense than that. But again, the fact that it's part of these provisions implies that people aren't doing it. Minimize exposed attack surfaces is a wonderful phrase which covers a huge amount of work underneath, potentially on a device. Basically, that means make your device more secure, which I suppose is a goal. Make sure personal data is secure. Examine system telemetry data. This is about whether a device that gathers information, and things like your mobile phone in your pocket, if you're using Google tools, you're tracking your location, how is that data stored? And could that be used to expose the device? And make installation and maintenance of devices easy. We don't have time to go through aspects of all of these, so I've picked out, see if I can count, 7 of those, and we'll see how these things can be, at least the goal of meeting these requirements can be done with some of the fairly standard features of an embedded Linux system. First thing we're going to talk about isn't a tool or indeed a Linux feature. It's a couple of projects which are used for tracking what are called vulnerabilities, which are project or device or software component specific issues that have been recognized and made public. And the CVE, the Common Vulnerabilities and Exposures Project, is used by vendors, etc., to disclose vulnerabilities. It's a public database that you can search, you can look. Let's say you're incorporating an open source library into your device, into your project. You can go and see what vulnerabilities it may have. That may lead you to decide not to use that component, or it will lead you to decide, well, we need to make sure we've got at least version X, because prior to that there was a vulnerability. The different vulnerabilities are classified into what are called weaknesses by another project, a related project, called the Common Weakness Enumeration Project, CWE, which last time I checked listed about 1,200 types of weakness that exist in not just software but hardware as well. So the example here is a few years old now, but it's from a package called sudo, which you're probably familiar with from Linux systems, used to elevate privilege so that a normal user can carry out certain operations. The particular version stated had an off by 1 error, which led to a buffer overflow, which allowed a privilege escalation beyond what should be permitted by sudo. And that off by 1 error is classified as CWE 193. So it's a way of easily sort of being able to compartmentalize, right, it's an off by 1. I know what that means. I understand what this vulnerability is. So these databases, the responsible companies and projects use these databases very proactively to make public vulnerabilities in their systems. I'm not saying all companies and organizations are going to do that. But we have a ready-made solution for a means to manage reports of vulnerabilities. You find a vulnerability in your device, you make it public, it's for the greater good, kind of the open source ethos encapsulated. Of course, in addition to this, as a vendor of a device, you should make it easy for your end users or your customers to report suspected vulnerabilities to you. That can be as simple as a an email address. Indeed, on the DoLoS website, in an effort to practice what we preach, alongside the usual sort of, copyright notices, if you find any potential security flaws, email security@dolos.com. Can be that simple. Looking now at tools and secure compilation, a good place to start in this discussion is actually looking at the a table that the CWE project releases every year, which is the top 25 most dangerous software weaknesses. This is from a year or two ago, and it's not the whole, as you can see, not the whole 25. We've picked out some of the top ones, which are particularly relevant for C and C++ programming. There's a whole bunch of stuff for things like SQL and other things like that, which are less relevant to our discussion here. And what we can see of these, that they're the usual things, the usual mistakes that people make when programming in C and C++ in particular. Out of bounds reads and writes, improper input validation, command injection, which can be quite easily done, integer overflows. These things, often they can be triggered in different ways, and often one thing will lead to another. That you can have an out of bounds write can then cause a heap or stack overflow, which then accesses uninitialized points, whatever it might be. There's lots of different ways that bad behavior can follow. I mean, what we're not talking about here is the other languages. There's been some discussion this week, of course, and in previous years about things like Rust, which should protect against a lot of these kind of issues. That's the theory, at least. So the first tool that we can use to mitigate against this is actually a macro provided by GCC called Fortify Source, or called Source Fortification, which is a rather grand title. What it basically does is detects buffer overflows in all the standard memory and string manipulation functions that are often the source of problems. So things like memcopy, memset, strucopy, strucat, sprintf, etc., etc. And it works at two levels, which is where it's very useful. If there is definitely a problem that is detectable at compile time, then you get a compilation warning, like you can see in the top example. So it will pick up those issues at build time. It also inserts runtime checks. So if there are things which are not always going to be a problem, if you like, but can be a problem at runtime, like a very trivial example at the bottom there, the buffer's only got 5 slots in it, and we're giving it a string with more than 5 things. Pretty naive, but it will pick up those runtime issues as well. You can perform 2 levels of checking. Level 1 shouldn't change the behavior of the program. Level 2 goes further but can cause false positives. So, there's a potential risk associated with that. Question?
Does it have a major performance impact?
It depends on your definition of the word major, I think, and it depends on how much you use these functions that it's checking. That's not much of an answer, but it can do. I think it's the best answer. It doesn't have to, but it can do. But like a lot of these things, a lot of the things we'll speak about over the next few slides, there has to be a trade-off with performance for security. And that's equally true of the next feature, which is a protection against what are often called stack smashing attacks, which is the set of stack protector options available in GCC. Again, different levels that this can be applied at. They all work using what's called a canary value. If you're wondering why canary, the idea is canary in a coal mine, the idea that the canary keels over before the miners do, maybe relevant given the industry of this area. It's basically a value, a random number which is written before the stack, and if anything overwrites that number, the implication is that it's also potentially overwritten the stack as well. So the different levels you can see there. Yes, there is a performance implication of these things, and that's why there are these different levels. And indeed, the fourth option there, I'm not going to go through all of them. If you have particular functions you're concerned about, you can use a little attribute just to tag those functions to be checked with the stack protector. So you can be quite selective about what you're going to do in terms of your system. Another feature which has been pretty standard in Linux for quite a long time is ASLR, address space layout randomization. It's been in the kernel since the 2.6 days. And what that will do is basically change how things are laid out in memory, which immediately makes it more difficult to exploit a potential weakness. If you can't predict where different parts of the program are going to be within the process address space, that makes life more difficult for any potential attacker. ASLR is normally on by default for most architectures. It can be switched off via an entry in the procfs. And it's normally, we can see the compilation options there, PIE, PI, position independent, executable. That is normally on by default in GCC, for example. Another type of attack is called a global offset table attack. It's basically about hijacking calls to shared libraries, which are resolved dynamically to get better performance. You can attackers can kind of reroute a call to a shared library to their own code. Basically, you can switch off these optimizations. Question?
Is that the mechanism that the exit exploit used? That was the reason?
I can't remember off the top of my head.
Because they introduced something that hijacked.
Yeah, I'd have to look up the detail. I don't remember off the top of my head. My brain is not functioning at its best this morning, I have to admit. So these options basically switch off these optimizations. Yes, things are going to go a bit slower, but you're going to be less exposed to risk. There are various open source memory checkers, runtime memory checkers you can use to verify the behavior of your programs. Valgrind is one you may have come across. Another one that's becoming quite popular is called ASAN, or the Address Sanitizer. This is from Google. Google never miss an opportunity to re-implement something that somebody's already done. But the ASAN tool is actually very powerful. It does have a performance implication. It uses shadow memory effectively, so you could be looking at maybe double the memory usage while you're running with the Address Sanitizer. But it will pick up bad behavior with respect to your use of memory, and is a really useful tool. It's implemented for GCC and for Clang, which is another useful aspect of it. Google themselves are obviously a bit sensitive to this criticism. They just redo what everyone else has done. If you find the GitHub page for the ASAN, there's actually a sort of table comparing ASAN with the other memory checkers like Valgrind and Mudflap and various others. So it's going to pick up things like buffer overflows, etc., etc. So it's another tool in the toolbox. Another really useful tool in the toolbox isn't a compilation tool as such. It's actually just a script. It's a script called checksec, which was written by one of the guys, a guy called Tobias Klein, that was involved in the GOT, the Global Offset Table vulnerability discussed earlier. It's now available. It's part of the Yocto meta security layer, for example. And it can be used to assess basically the security status of an individual binary, a compiled binary. Do you have stack protection in place? Do you have position independent executables, etc., etc.? Or you can actually run it on running processes. in a system, and it will tell you the status, which options have been used. And even it has a kernel configuration checker that you can see what security features you do or do not have within your kernel. So it's a really powerful little tool that you can use to assess your system, your binaries, your running processes, your kernel, for how secure these things are. Really, really, really powerful little tool. So some of the things like seccomp we'll talk about in a moment. So all of these things, it's things like validating input data, minimizing exposed attack surfaces. It's about doing what we can do to make our programs more secure and less vulnerable to attacks. In terms of a Linux system, there's a whole bunch of things that we can do. And the first of these is fairly standard, not fairly standard, very standard access control. Every Linux, every Unix system has it. Effectively, it's a two-stage process. You have an authentication stage. Are you who you say you are? And then once you've identified who you are, what are you allowed to do? An authorization phase. And in a kind of threat model diagram, the sort of dashed line is often what's referred to as a trust boundary. You're crossing over a trust boundary. So the authentication either is something that you know, a password or a PIN, something that you have like a key or a certificate, or something that you are, a fingerprint, for example. These are all ways of authenticating your identity. Once that identity has been recognized, we then move into an authorization step. You are who you say you are. What are you allowed to do within that system? And I guess this feeds into the idea, if we're going to trust this authentication, we have to have unique passwords. We have to have passwords which are allocated dynamically, not set when the device is manufactured, and so on. So the standard model of users, groups, permissions, often referred to as discretionary access control, DAC, from Unix into Linux. I'm sure we're all pretty familiar with this at a conceptual level. It's the first stage in making sure things are protected within the system. It's about making sure that permissions are set appropriately. It seems trivial and naive, but problems occur, particularly with things like, there was a problem a few years back with an Android system where nodes in dev on this particular device, so device nodes, had improper permissions set on them, which left that device exposed because the permissions had not been set properly. It happens. In addition to a discretionary access control, most Linux systems also have what's called a mandatory access control mechanism, an MAC. DAC is static in nature. You have a user ID, a group ID, you have a set of permissions. MAC is a dynamic checking, and it works in a different way. It's in addition to DAC. If you don't pass the DAC check, that's game over, but then you pass into the MAC checking. In Linux, slightly bizarrely, actually came from the American NSA invented these mechanisms back in the late 90s. They were using Linux for their own data systems, and they wanted to implement what's called a multi-level security, an MLS system. The idea of secret, top secret, eyes only, if you read this, you will be shot kind of security. And the way they implemented that was a mechanism called SE Linux, Security Enhanced Linux. And maybe surprisingly, they actually open sourced that implementation, and it was integrated into the Linux kernel about, over 20 years ago now. The way that it works I mean, maybe in contrast to the liberal democracies that we're all generally very happy to live in, we tend to have in our lives a list of things you can't do, and everything else is, perceived to be okay. The way that MAC works is that you have a list of things you can do, and anything that isn't on that list is not allowed within that system. So you have an explicit list of operations which are allowed. And it works, as we can see in the diagram, that you have a subject, a process, that makes a request to access some sort of object, a file or a resource, and based on the attributes that those subjects and objects have, that will either be allowed or not allowed by the administrator of the security policy. So this SC Linux was the original one of these. It's still used for things like Red Hat, Fedora Linux, and heavily in Android as well, as we'll see. There are others, and the way that it's handled in the Linux kernel has changed over the years. It's now a very modular implementation. So we have a set of different, what are called LSMs, Linux Security Modules. Module in the normal sense, not an LKM, not a .ko in the kernel. And you can basically, when you build your kernel, you can choose which LSM you want to use. And you can plug in a set of what are called minor LSMs, which are kind of single feature, single use MAC controls as well. And then the kernel has a set of hooks, and that will call into the policy that's been implemented. So the main LSMs that we come across, SC Linux, we mentioned the original, still used, as I say, in Red Hat, Fedora, and in Android. Very heavily used in Android. The whole Android security model is built on SC Linux. Bit of acronym fun there, but you can do what's called domain type enforcement, or you can do role-based access control, or you can do multi-level security with SC Linux. So it's very rich, very complicated. It has a set of predefined policies, and the main issue is that they typically will not work on your system. You need to go through a process of sort of, not even, tuning implies that it nearly works. You have to go through a process of making it work in your system. AppArmor is if you use Ubuntu, you're using AppArmor, if you weren't aware of that. It kind of at one level works in the same way, but rather than using labels, SC Linux is built around labeling processes and subjects and objects. AppArmor works on paths. On a simple system, there's an MAC mechanism called SMAC. The S stands for simplified MAC kernel. It is much simpler, but you find that if you want to do anything too complicated, you end up almost rewriting SC Linux in SMAC rules, so it's kind of pointless. It's used on an OS called Tizen from Samsung, which has kind of died, I think. I think they may still use it on some of their smart TVs, but it's not really gone anywhere. Another one, Tomoyo, I don't know much about. One thing that's interesting about it is that it has a policy generation phase. So you can basically run the system in a mode where you go through all the normal things you want to do with that system, and it will kind of capture that and turn it into policy, which is quite an interesting idea. But I've not had the chance to play around with that too much. So all of this is about making your system as secure as possible. And a phrase that often comes up with these things is designing to the worst case scenario. It's assuming that things are going to go wrong in your system, and what can you do to limit any potential problems. This is about protecting secure data, protecting sensitive data, making sure that processes can't be, even if a part of the system is exploited, stopping it from being broken out of where it exists into other parts of the system. Something else which is very commonly used to make Linux systems more secure is some sort of containerization or virtualization, where we have separate instances effectively running in some sort of sandboxed environment. This simple example is using a mechanism called LXC, which is a fairly one of the original containerization implementations, quite low level, quite simple to set up. And the way that it works is using underlying features like C groups to isolate resources and namespaces for namespace isolation, so that within a container you can limit what processes within that container can see in terms of the overall file system, and you can limit what resources they can access. And so an example from a customer that I worked with was a radio system for train engines, which was not online in normal use, but they needed a maintenance mode which could go online. So they had two containers, one for the normal use case and one for the maintenance mode. And the normal use case had no internet connection, effectively. It leads us to this idea of what we could call a full container, which is a sort of fully featured Linux system with an init program, and what we can call a lightweight or an application container, which just contains one or a few processes which are just running in this very tightly sandboxed world. You know, maybe the services related to billing within your system are inside a container. That data is not accessible from elsewhere in the system. It's about the attack surface. Most of these things are about, as I say, designing to the worst case scenario. I mean, the idea that, you know, I don't know, one of your kids, you go on holiday and one of your kids leaves one of the windows open at the back of the house. If all your internal doors within that house are locked, then the effect of somebody getting in through that open window is going to be a lot less than it would be otherwise. And that's what we're looking at in a Linux system. There are various things that can be done at a file system level to make a system more secure. This is one slide that covers a lot of potential complexity. The two aspects of file system security that we're interested in are encryption, so that you can't access data, and integrity checking, so that you can be sure that data has not been tampered with or compromised in some way. And in Linux, we have two ways we can do both of these things. We can do it at a file system level, a per file, per directory level, with, for example, fscrypt, fsverity. These are implemented in file systems that allow us to, for example, encrypt a particular directory so that only people with the relevant keys can access that data. Or you can provide what's called integrity or verity checking on individual files or directories. Or you can work on the whole device with a block level encryption or a block level verity checking using a subsystem called the device mapper framework that the kernel provides. And it's this mechanism that sits underneath things like Android verified boot. A lot of the boot verification systems, file system images are checked to see if they've been tampered with before the boot continues. Obviously, software integrity, secure storage is paramount here. Another tool that we have, and again it's about reducing the attack surface, is a feature of Linux called seccomp. Stands for Secure Compute. These days it's implemented using Berkeley packet filtering, BPF filters inside the kernel. It's basically a mechanism for controlling what system calls a given process can do within the system. And you can have quite fine-grained control. You can work it in either direction. You can say whether you can do anything apart from this list of system calls, Or you can say, these are the system calls you're allowed to make. And you can even filter on the parameters. So you can very fine-grained control over what system calls a particular process can make. And it's about, as we've said, it's the worst case scenario. If you have a particular part of your system which you feel is exposed, then using something like seccomp can limit the effect of somebody attacking or attempting to exploit that particular process. If it tries, so you have a parent process that sets up the filtering via a library called libseccomp, set of user space APIs. That then establishes the filters inside the kernel, and then it launches a child process. And if that child process tries to do something which isn't on the list, it is immediately terminated by the Linux kernel. So it's prevented from doing things it's not supposed to do. Limiting the attack surface quite heavily. In terms of the kernel, one point to bear in mind, we spoke about the CVEs earlier. There are lots of kernel vulnerabilities listed in the CVE databases. These graphs are from a website called cvedetails.com, where you can just search for Linux and it will show you what there is. But we need to bear in mind that a lot of vulnerabilities in the kernel never make it into a CVE report. They're discovered and fixed by the kernel maintainers without ever featuring as a CVE. There was a case a few years back now where Google requested a whole bunch of fixes for the kernels that were going to go into their Pixel phones running Android, and about 90% of those fixes never had a corresponding CVE record. But I suppose the message is, make sure that you're keeping as up to date as possible with your Linux kernel. I despair when we get customers on our training classes saying, oh, yeah, we're using a 2.6 kernel or a 3.0 kernel. Normally it's, well, that's what our board supplier gives us. And you have the conversation of, well, either you need to figure out how to get a more recent kernel, or you need to think about changing board supplier, if that's how out of date they are. It's an ever-changing picture. Keeping your kernel up to date is the best advice that we can give. And using an LTS, it says there, apply all stable and LTS bug fixes. The long-term support kernels will have important fixes backported. And there's also a project not mentioned here called the super long-term support kernel, which is backporting fixes for 10 years plus on kernels. So if you're working on a project with a long lifespan, have a look at the SLTS. It's part of a project called the Civil Infrastructure Platform, run by the Linux Foundation. Just ask me if you want more details on that. That is a really good option for, industrial equipment or whatever. I think off the top of my head, it's a 419, I'm going to say. It might be 414. They have a wiki page with a table that shows you the EOL of those SLTS kernels. In terms of your kernel configuration, the first piece of advice is take out as many features as you can from your Linux kernel. Take out all the stuff you don't need. Anything that's there that's not being used is a potential flaw or a potential weakness. There's also a bunch of options, many of which correspond to those compilation options we saw earlier. Things like stack protection that you can select via kernel configurations. Also reduce the amount of information that your kernel provides. Switch off dmessage. Do you need it in your production system? Any information about the system is a source of information for attackers. We've put this one, config devmem, on there, almost as a sort of horror show. Devmem is a mechanism that lets user space access physical memory directly via an entry in dev/dev/mem. So it's a massive black hole in the security of any device. It has been seen on production devices. So switch that off as well. Again, we're minimizing our attack surface as much as we can. Linux kernel modules obviously provide a lot of flexibility within your system, maybe for loading drivers when they're required, reducing the size of the kernel so that your system boots faster and things like that. But they are a potential attack vector. And so the first question to ask is, do you need to load drivers, etc., as modules? Or can they be built in? If it's a fixed hardware environment that isn't going to change, why are you loading the driver as a module? Other than, I suppose, potential licensing nervousness, let's say. If you do need to load modules, then the kernel provides module signing, and that's really the way to go. With some kernel configurations and setting up keys, basically only modules with the correct signature will be loaded. So that protects you quite strongly from people trying to load their own modules into your system. One of the LSMs, the minor LSMs that I mentioned earlier, can be used in conjunction with that. It's not mentioned on the slide. It's called load pin. It prevents you loading a module from an alternative file system. So it stops somebody from plugging in some extra storage and trying to load modules from there. Module signing, software integrity.
I understand there's a mechanism that you can, so that you load modules during boot, but after boot you turn off the mechanism that allows module loading.
Yes, you can control it. I can't remember exactly. It's probably in the procfs. There's a switch somewhere that you can use to switch it off. I can't remember exactly. Yeah, that's another option, yeah. In terms of the boot process, boot time is a dangerous time for an embedded system. There's a persistent threat that things are going to be exploited. Malicious software is going to be inserted at boot time. There are various mitigations that we can see there, some of which we've already mentioned. Secure boot process being the main one of those. And there's a lot of rather glib phrases that are used in association with this, like chain of trust and root of trust and things like that. But that's really what most of the secure boot mechanisms are built around. There has to be some point that you trust 100%, and everything else can build on that point. So a standard boot is potentially open for attack at multiple phases. Depending on your SoC, you have some sort of ROM boot that then maybe loads a first stage bootloader into some on-chip memory. Do you know it's the right first stage bootloader? No, you don't. That then loads a second stage bootloader, typically U-boot. Is it the U-boot that you think it is? Has it got extra features that you weren't aware of? That then loads the OS. Well, it's just an image file. Do you know it's the right image? A secure boot works on, as we say, having what's called a root of trust, which is some key value which is stored in some secure storage, a TPM, or fused somewhere in the hardware, which allows you to authenticate the next stage. And then once you've authenticated the next stage, you trust that, you can move on to the next stage and the next stage. That's the chain of trust. At every stage, you have a signature and a public key that you can use to check that signature, basically. And this is where the chain of trust comes in. You trust that initial value in pale blue, and you can then trust all subsequent stages of that boot process. And that's the standard mechanism that's used for a secure boot process. As it says there, it all depends on this root of trust. And it's about software integrity. U-boot itself, similar to the Linux kernel, it's a software project, effectively like the Linux kernel. It's a bare machine program that runs on ARM or ARM64 or whatever, and it has CVEs. You can find them listed. Try and use the most recent version you can. And there are a bunch of other things you can do. One of the things that we see a lot with U-boot is that during development, you tend to have a very flexible boot strategy. You want it easy for your developers to boot the target. You can load a file system or whatever from an SD card or a USB stick or whatever it might be. All of that needs to be switched off in the production system. Make it as simple as possible, effectively. You can only boot from one storage device. There's no choices in that. And indeed, you may be familiar with U-boot, press any key to get into the U-boot shell. Switch that off. You shouldn't need a shell in production. U-boot uses environment variables. These can be loaded, for example, from a text file. That's a security problem. What you can do instead is you can compile the environment variables into the U-boot binary for the particular device, and then they're fixed, they're immutable, they can't be compromised in any way. Another scenario, the last line of the table there, is what happens when things go wrong. And there have been cases where corruption of a storage device meant that a boot image was not loaded and the system was left in an open state because it wasn't handling that situation properly. And somebody could come along and load their own kernel onto that device. You're probably getting bored of these boxes popping up. It's the same things over and over again, really. Very brief word on vendor support. Modern SoCs have a huge amount of features for securing the system of varying degrees of complexity. Obviously things like cryptographic acceleration, random number generation, says their root of trust, providing a secure storage area for a key or keys. Even some devices, more advanced devices, provide resistance to sort of hardware hacking, power signature analysis and things like that as well. So it has to be an important part of the conversation when you're choosing what silicon to use for your particular project. So we're coming up to the time. We've really only scratched the surface of a huge topic. We run an embedded Linux security class over 4 days, face-to-face, and that only scratches the surface of it. So in less than an hour, of course, we've only highlighted a few issues. That second bullet point is one of the most important points, I think, of the whole presentation. You've got to design in security from the start of your project. I despair at the times where we speak to our customers. Yeah, we want to take the Linux security class because we finished our project. Now we need to make it secure. And that is just an upsetting conversation to have. Having a secure development lifecycle from the beginning is key. This little flow on there, it's common sense at one level, but that's the kind of flow that we need to have. And note, it doesn't finish with the release of the device. There needs to be a feedback loop in there. What happens if a vulnerability is exposed on your device? How will you deal with that when it's out in the field? And these frameworks like the ETSI standard can guide you. And in certain industries, there are, actual provisions that you need to demonstrate that you're following, in automotive and so on. It's something that's being backed up by legislation as well. The legislation to provide a software bill of materials for your device so that everyone can see what components you're using and can see what vulnerabilities there are. This is all coming into our industries. And the hardware vendors are providing more and more security features, and we should make use of those. We should exploit those as much as we can. Okay, that's it from me. Thank you very much indeed. the voice held up just about there, I think. So thank you. Go on.
So you mentioned some older versions of Linux kernel might not be secure. A lot of Android phones they ship with, even recent ones they ship with 4 point whatever, so it's quite old. What is does that mean we should avoid those phones, or what do we do?
No, well, that's an interesting question actually, because I've got a Pixel 5,
Yeah.
which is running Android 14, which is the up-to-date version, but it's running a 4.14 kernel, but it's running a 4.14 Android kernel, which is not a mainline kernel, and they backport more features. They take the LTS mainline kernels and they backport even more to maintain those kernels. Yes, newer is better, but I think, I'm not going to make promises, but I think an Android kernel is going to be more secure than the equivalent LTS kernel. Yeah, it's interesting. Even though individual Android versions say we support kernel, 5.5, whatever, 6.0, depending on the handset or the device, it may be an old one. But Google are pretty good with security. They put security updates out every month with all the CVEs that have been fixed. They're very public, unlike other mobile phone manufacturers, let's say. Okay. Ooh, at the back. Yeah, that's true. And there's lots of different interfaces to the CVE database, none of which work that well. CVEdetails.com makes it a bit easier. The other mechanism, if you're using Yocto to build your system, which we would recommend that you do, it has CVE scanning built in. So for all the packages in your system, it will poll the database and give you a listing of the potential CVEs that you have. It's a reason to use Yocto. There are plenty of commercial companies out there as well that will sort of sell CVE checking services or systems to you as well. But yeah, there's no easy way to do it. There's an element of just work, boring work, I'm afraid.
You said the SC Linux is used as the Android security model, the base of that. Does that mean like they limit the number of system calls you can make, or is that what the base of this?
Yeah, it's so the Android security model has various aspects, but what there is with Android out of the box is a whole set of policy, as it's called, a whole set of rules that says this particular part of the system can only access A, B, and C within that system. This process is a HAL daemon, whatever. It can do this, this, and this. It can only access files in that directory. It can only, whatever it might be. There's a huge amount of policy that comes with Android out of the box. So if you're extending Android, you have to add in your own policy so that your things will work. Okay, great. I'm going to switch off the mic.